Good morning, everybody. Good morning, Professor Van Westen. Thank you. My name is Hui, and I'm glad to coordinate this series on environmental and human health risk assessment. Today, we listen to Professor Van Westen. He's from the University of Twente in the Netherlands, and he's talking to us about analyzing changing multi-hazard risk for decision-making, and I look forward to his lecture. But before that, I just want to talk about a technical issue before. Some of you might be participating to the series for the first time. So when you enter, this Zoom conference platform, we set up to the fact that your microphone is automatically muted just to prevent background noise. And so if you have any questions, you have any comments, and you have any thing to share with us, just feel free to turn it on before you want to start speaking. And then you have another features of raising your hand as well to attract the attention from the host and from the speaker. It is just in the participant panel, so you can open the panel and then just click on the buttons. Raise your hand so you can show your attract the attentions. As well, if in the case that it's not convenient to speak, you can feel free as well to type your questions in the chat option so that could, a message gonna be pop up to us, and then we'll try to reply to your questions accordingly. And so let's go back to the lecture of today. Professor Van Westen is going to talk to us about analyzing changing multi-hazard risk for decision-making. And I just want first to introduce the profile, the research profile of Professor Van Westen. So Professor Van Westen is currently an associate professor at the University of Twente in the Netherlands. His research focuses on research sensing and geographic information system for natural hazard and risk assessment. He's obtained his master degrees from the University of Amsterdam and his PhD from the Technical University of Delft, both from the in the Netherlands. And from 2005 and 2015, he was the director of the United Nations University, the ICT Center on Geoinformation for Disaster Risk Management. He has published more than 100 scientific publications, authored 17 books, 26 book chapters, and on his work has received more than 11,000 of citations. His research interests focus on four main pillars that I just try to summarize it here. The first one is about disaster risk management, and is from different aspects on landslide hazard and risk, on volcanic hazard and risk assessment, and technological risk assessment. So he has conducted several projects all around the world, and I don't have the room to cite all the country he has worked on. So just try here to summarize some continents that you can see in the PPT. The second research focus is on national scale risk assessment, which is very impactful. And on a practical aspect, he's developing methods for the analysis of changing multi-hazard risk, and he's providing tools for decision makings for the planning of risk reduction measures. So with all this expertise that Professor Van Westen has over his career, so I do greatly looking forward to listen to his lectures on analyzing changing multi-hazard risk for decision making. And thank you again for your agreement to do these lectures to us. And I just turn the stage to you. Thank you, Professor.
Okay, thank you very much. So I will now share the screen, the presentation. Hope this is working fine.
Yeah, it's working totally fine.
Okay, good. So good day, everybody. For me, it's good afternoon. It's by 2 o'clock, so probably for you it's quite different. So thanks for listening in. So thank you for the organizers. I'd like to do a presentation during this 3/4 of an hour that introduces you to multi-hazard risk and why we actually use to assess that, and also the problems involved. and we eventually want to do this work for decision making on disaster risk reduction. So I'll be showing you a number of examples of the work that we're doing, plus also an overview of a number of concepts. Before that, I do that one slide of introduction of my my university. University is University of Twente, but I work at the Faculty of Geoinformation Science and Earth Observation, called ITC, which is a bit of a different faculty than all the others. We have been founded by the Dutch Prime Minister of after the Second World War as an Institute of Development Cooperation. So we do international training, research and project services all over the world, focusing on capacity building and institutional development for geoinformation science and Earth observation in developing countries and emerging economies. So we have basically no students from the Netherlands, although that has recently changed because we are now also offering a master program in spatial engineering, which is also for Dutch and European students. Our regular master program of 2 years is on geoinformation science and Earth observation, and that focuses on a number of different themes, including disaster management, food security, smart cities, water management, biodiversity, and governance. We collaborate in international platforms. As was mentioned already, we used to be a center for the United Nations University up to 2015. And now we are an expert center within the Integrated Research on Disaster Risk, IRDR, where we have now an expert center on spatial decision support systems for disaster risk reduction. Related to also distance education courses, maybe this might be interesting for you, as we run every year a distance education course on geospatial data for multi-hazard risk assessment. This is roughly a 6 weeks course, which does not contain any real-time lectures as I'm doing now, but it's very focused on practical exercises using geographic information systems, open source, and which has a theory book and an exercise book, and which guides you through different steps of multi-hazard risk assessment. If after this course you would feel like you want to learn more about this topic, search us on itc.nl/study and find distance education courses related to this topic. So my topic of today, to go now to the real topic, is related to evaluating and analyzing risks. And as you probably have heard in the earlier 2 lectures that were given, risk is defined as a probability of losses, or in other words, estimated losses per time period in a given area. So this is also a component, a spatial component that's very important within the whole risk assessment procedure. And it is generally determined by analyzing 3 different components. A component called hazard, a component called elements at risk or assets, and a component called vulnerability. Within my presentation, I'd like to go through these different components and later on see how these are combined in a hazard and risk assessment. So the hazard component, to start with, has very important temporal probability, so a chance that it might happen within a particular time period. Think about an earthquake, about a flood, about a forest fire, for example. They may occur with a certain frequency, and say different events occur with different magnitudes and frequency relationships. And so what we are trying to establish is different events with different frequencies and model the consequence of that. So that depends very much on the hazard type. So these types of models would be different for different hazard types. And also there are differences in things like duration and onset time. One of the important components within the hazards would be the hazard intensity, which would be the spatial distribution of measurable effect of the hazard. So be it, for example, flood height or earthquake acceleration, which you could model in a GIS, a spatial model over a particular area, and that has different values for different locations. This in combination with elements at risk, so those would be all the objects or the processes or features or population or animals that would be at risk to your hazards. They might be exposed if they are located within the hazard footprint areas. And so what we do is an exposure analysis of spatial overlay of your hazard footprints and your elements at risk. Now these elements at risk could be, say, very many. And so in the risk assessment, you would have to determine initially what is the aim of your risk assessment. Are you looking, for example, as a tool for early warning? Or is it for risk reduction planning? Is it for future developments? Is it specifically for one sector, like the health system or transportation system? So that would determine very much which elements at risk you're looking at and how do you collect those information. You need to characterize them as well and quantify them. This could be a quantification in number of elements at risk or monetary values, or it could be expressed as a number of people. But the way in which you express your elements at risk is also the way in which you would express the risk eventually. So one of the most difficult components within the risk assessment is the vulnerability, which is the relationship between the hazard intensity and the degree of damage caused by that hazard intensity to one specific type of elements at risk. This is generally represented through graphs or curves that represent the damage in relation to the intensity. So, for example, every element at risk type would be characterized by one of these curves, and you can basically translate then the intensity into the degree of damage for that particular element at risk. So we need to look at all these individual components, and we also need to do this spatially. So let's look first at one of the main components, and that would be the hazard part. So when we consider hazards, we have to ask ourselves a number of questions that need to be answered. Say on the what, where, how often, how severe, how much area, etc. So we first need to look at what the hazards are that are exposing, that are endangering a particular area. So we need to do an inventory of the hazard types, and we need to also look at how they interact with each other. Very important is the where component. The hazards are spatially different, so we would like to analyze the areas that might be affected by hazard events, and we do this also by looking at past events and through modeling. We want to know how often they happen, so we need to have an idea of their temporal probability, and for many of the hazards this is also done by correlating historical events with the number of times that they happen and the intensity or the magnitude that was caused. For example, discharge from a river or earthquake magnitude, and then counting how often these events with the same magnitude occur over a number of years. Definitely the longer period there is available, the better your probability estimates could be. The severity is generally mapped as hazard intensity, if that's possible, and expressed as hazard footprints for each return period. If we want to use it also for particular early warning applications, we also need to know the warning time that is there. The hazards need to be analyzed, say, both in the present situation, but also if something changes. And the figure on the lower right side is showing a debris flow event modeled with a runout model, as it's called. So how the runout will affect an area downstream, and will it reach the village that is there, yes or no? And then by putting in the red deflection dike, you could also model how much a particular risk reduction feature would change the hazard. So hazard susceptibility maps are generated for different types of processes. Here you see one example. This is a job we did for the country of Abkhazia, which is in the Caucasus region, that has also experienced quite some problems with landslides and debris flows. Here, this is a typical example of a susceptibility map that indicates whether landslides are likely to happen, and if they happen, whether they are likely to move down, but not with a particular magnitude frequency information. This is partly because we lacked enough data to express that for this type of hazard. This makes it also more difficult to use them in the risk assessments, because we have more difficulty on saying, okay, what would be the chance that a landslide happen within a particular part of the terrain. For other hazards, that might be much more different. So for example, flooding hazards, here we see typical flood hazard maps for an area, also for the same area in Abkhazia, where we see flood intensity maps, so basically flood height maps, and each one represents a different probability of occurrence, so a different return periods. These are modeled with different inputs in terms of rainfall, and then through a hydrologic model, it's modeled how much water is expected. Another example of such an intensity and frequency information. So for earthquakes, what would be the expected ground acceleration based on seismic models? And so we'd be able to, with these types of maps, generate, say, for each return period, also a hazard map, and correlate that with, for example, buildings to estimate the number of collapsed buildings per return period. Now, many of the hazards are quite complex. They are having rather complex relationships. And so this is something that needs to be taken into account when we do this risk assessment. Multi-hazard risk means that we have a risk of probable losses from different hazards. These could be completely independent hazards, like a technological hazard, and on the other hand, a flood hazard. Wait a minute. I hope everybody sees my presentation. Yeah.
Yes, Professor, we are seeing it, but maybe we are seeing the second screen.
Okay.
Yeah, with notes and next slide, so it's a little bit small. I just wonder if you could swing back to the main one, please.
Yes, I can probably switch them around if that would be.
Yeah, it's perfect.
Is it now better, or is it the
no,
same?
It's the same. It is the same. I think it's the second one.
Let me do it the other way around. Still the same?
Yeah, I think you have just to redo the sharing screen screen by clicking on the first screen. I'm sorry for that. I think it's just because you have two screens.
Yeah, I will share it again. Okay. Wait a minute. Better, or is it still the same?
It is
Okay,
still the
Professor
same.
Van Westen, you may try the display setting. When you share the screen on the top, there's a display setting.
Yeah. Well, I will just make it one screen then. That's easier, right?
Now you just click on the display setting. You can switch the plane, like your screen, so you can see over there then.
Shit.
Yeah, it's
Okay.
perfect. Yeah, it's perfect. Thank you very much.
You just do it like this, right?
Yeah, yeah.
Okay.
Yeah,
Sorry.
I apologize. Yeah, sorry.
Okay, so I was explaining about these different multi-hazard relationships. So they could be completely independent. And in that case, you can actually calculate the risk for the two events separately and add up the risk. Although in many different cases, that could even be a problem. You would say like an earthquake and a flood is completely independent, but in the next slide, I will show you that's not always the case. Coupled events is another one. So you would have the same trigger. For example, strong rainfall might trigger a debris flow or a flash flood. And the same village could be affected by both. And so adding up the risk and the losses by these two would be wrong because you would be double counting. The third is actually a conditional hazard. Hazards have a relationship that are conditional. That means one hazard changes the condition so that later another hazard is more likely to happen. Think about, for example, forest fires, which would change the conditions of the terrain surface and make the terrain more likely to produce flash floods and debris flows if there's a rainfall event after the forest fire, some weeks or months later. The most complicated type of interaction of multi-hazards, also for the risk modeling, would be the domino or cascading hazards. As the word says, a domino stone actually topples the next one. So you would have one hazard that triggers the second, the third, and so on. Now let's look at a few examples of those to have a better idea. So one of the examples comes from China, where we did a lot of work after the Beichuan earthquake in 2008, which produced a huge amount of landslides during the event itself, and also later on had a lot of problems in the 10 years after. We produced an atlas of all these events. If you're interested, go to the Flipbook site and you can actually find this atlas. So the event, say the multi-hazard relationship is demonstrated in this picture. The earthquake generated a large amount of landslides during the event. Number of them blocked the valleys. So at least 35 complete damming locations were mapped, and rapidly lakes were formed afterwards, with the danger of breaking out because these landslide dams were unstable, and this would produce huge debris flow or flood downstream. So there was in that particular area a major city called Mianyang of 2 million people, and the authorities had to decide, do we have to evacuate that city because it might be flooded? Yeah, so these kind of decisions require, say, a risk assessment, and also to be based on a multi-hazard assessment that should be done in a fast way. So it's multi-hazard because it's a chain of events. We have an earthquake causing a major landslide, blocking a river, and eventually the hazard that is destructive for the city is the flood. So they work in chains. So you need a series of models that run in sequence in order to do this analysis. Here you see one of the the results from it. The flood model that we run after doing the dam break model indicated the flood height and also the arrival time that the flood would take to reach the city. Another example related to that same event are debris flows, which would happen mostly after the event, also because some of these lakes break out or because of intense rainstorm events. They are very destructive, and they also affected areas that were already reconstructed after the earthquake. So this is illustrated in the picture on the right side, where you see on a alluvial fan, you see a reconstructed town, part of a village, which was then affected in 2013 by a debris flow that wiped out all the red indicated buildings. I say modeling that or predicting that beforehand is very difficult, also because temporally it changes over time. So there's about a time window of 10 years before this activity basically becomes less. Another example of such an event, so the city of Yingshu, in the epicenter of the earthquake, with a major river running along the side and a debris flow coming out of the channel on the south, basically blocking the whole river, which then flowed through the city itself. So these type of hazards are very difficult to model and to predict. Another example, coming more now from hurricane-related environments, is from the Caribbean, where we did a project for 5 Caribbean islands, and where we mapped the hazards within these islands for major hydrometeorological events. We also shared all the data on a web portal, and we train people on how to use this information for spatial planning and infrastructure management. So this project resulted in a series of multi-hazard maps for these 5 Caribbean countries, and we did modeling related to flooding and also to landslides. Here you see 2 examples, one flood hazard map on the low left side and a landslide susceptibility map on the right side. These are built up from, say, historical inventories from past hurricanes. Then in 2017, September, maybe you remember that there was a major hurricane in the Caribbean, which is called Maria. This was causing a large amount of damage within the island of Dominica, and we did a mapping for UNOSAT and UNITAR, which is the United Nations satellite organization, to map the affected area. So all the reds are the landslides and the blue are the debris flows. The hurricane itself, therefore, is producing a number of multi-hazards that are during the hurricane itself problematic, but are also in the years to come, because the hurricane wiped out most of the vegetation on the island and produced many landslides that have a lot of sediments that could be moved in the next event. So one of the issues that we were looking at in this particular case was the use of a multi-hazard model. So a model that would allow us to analyze all these different processes at the same time. So for example, the landslides coming down the slope, how they mix with the runoff and produce either floods or debris flows, but also, say, the influence of waves from the sea on the flooding effects inland. So this model we developed over the last years. It's called OpenLISEM. And you could also, if you're interested, it's open source, it's free software, so you can have a look at it. So just a few examples how it works. This is a simulation model on the right side. Oh, sorry, that seems to have a problem. No, it works. We see a simulation now running of, say, the runoff and the sediments that move through the part of the island. And on the upper left side, we see it as an animation as well. You see at some stage, the brown areas are the landslide areas, whereas the blue areas are the flooding areas. So the interaction between landslides and flooding within the same area is modeled using such type of multi-hazard models. So to come back to our risk assessment concept, say the hazard part is a difficult issue. The elements at risk part, on the other hand, are perhaps less of an issue, although it's more a fact of mapping them using either remote sensing information, VGI, voluntary geographic information, for example, using OpenStreetMap for getting building footprint data. And so there are a lot of different tools available now that help us to do this element at risk mapping, although the characterization of them, these would be still problematic. So we combine those into a risk assessment approach. And so the scheme here indicates what are the different components of that risk assessment. With different colors. We see the green part being the input data, and the yellow part being the susceptibility and hazard assessment, whereas susceptibility is more indicating the areas that are likely to have a hazard, whereas the hazard assessment is translating that actually in probability terms. And we have an exposure analysis where we overlay the elements at risk with the hazard footprints, and followed by the vulnerability assessment where we establish intensity or magnitude damage relationships. And then these are all inputs into our specific risk scenarios. So we want to have a number of different scenarios where we correlate then the probability of the hazard event with the losses that are calculated as the vulnerability multiplied by the quantified exposure. Depending then on whether we can actually quantify, we either go through a quantitative risk assessment track or a qualitative risk assessment track. And we use that information to design our risk reduction measures. Now, for the risk assessment approaches, there are several options. We could go for quantitative or qualitative approaches. And so basically 4 main approaches could be found. Indicator-based approaches are, say, qualitative, purely qualitative. The risk matrix approach is, say, semi-quantitative. We do want to express frequency and impact, but in classes. And the upper 2 are quantitative approaches, where the event tree analysis is more looking at sequences of events in a cascading sequence, and the quantitative risk assessment is the method that we mostly use for for the spatial analysis. So the indicator-based approach is where we trying to capture all the components by indicators. So hazard indicators, exposure indicators, vulnerability and capacity indicators. We score and weight them, and we make a qualitative index. We mostly do this using a tool called Spatial multi-criteria evaluation. The risk matrix approach is where we evaluate the frequency of events against their impact. And so we establish classes of frequency and establish classes of impact, and the combination of the two will determine the risk. Example of that is given here. You would have a number of buildings here that might be affected by a debris flow, and the combination of frequency and consequence or impact would be in a high risk situation. So red would be unacceptable and green would be acceptable. So when we then build risk reduction measures, for example, deflection dikes for that, our risk changes from initial undesirable situation to a tolerable risk situation. But on the other hand, because we do these measures, the processes in other areas might reach further. So you might have a situation in other areas where the risk also changes. And that is the spatial effects that we should always keep in mind. Now, what we're trying to do in most of the risk assessments is that we trying to model for a number of different hazard scenarios the relationship between the temporal probability, so the probability of the hazard scenarios, and the losses. And we plot those in what we call a risk curve, where we have temporal probability versus the losses, and where we assess the area below the curve as the average annual losses. So this could be done by doing this for monetary losses, and then we get risk curves that would represent probability of monetary losses. But we could also do this for population losses. Then we have the number of fatalities against probability, which is the basis for deciding whether the risk is acceptable or not acceptable. So graphs like that you see on the bottom right are designed and determined in different countries. These are country specific because they depend on policy, on which level of risk is acceptable and which level of risk is not acceptable. So this kind of population risk is the basis for decision making on whether risk should be reduced. Some rapid examples of these kind of tools at different scales. Here one example at the country scale level, so we can do a risk assessment at many different levels. So it's a work we did in the country of Georgia, in the Caucasus, where we looked at hazard of risk for 9 different hazard types, represented on the left, and on the right, a number of different elements at risk. In the middle, you see different levels of administrative units, so that we could both calculate exposure, so how many buildings are exposed to earthquakes, or how many people are exposed to flooding, etc., but also try to express that, say, in terms of how often that would happen, so probability of losses. We also use then that information in a separate vulnerability assessment, where we also look at different characteristics of these administrative units. We need a lot of information for that, and so also build it a web platform for that, where general public and also organizations could report hazardous events, as they are essential for doing a good risk assessment, where we can visualize the historical information per hazard type. We could use the system for evaluating the hazards and also analyzing exposure and risk. Then administrators from different administrative unit levels can generate a risk profile for their own administrative unit, which would indicate what are the hazards in the administrative unit and how much exposure and risk is there for different hazards and different elements at risk. We also produced an atlas, which you could also find on the internet as a flipbook, presenting the methodology. And we did also at the end a holistic vulnerability assessment. So looking also at all different indicators that relate to physical, social, environmental, and economic vulnerability. And so saying, okay, well, which areas have the highest risk, but which are also most vulnerable in terms of those indicators. The risk assessment using quantitative methods is illustrated a bit more in this picture. We have hazard scenarios, for example, modeled flood depths or snow avalanche or whatever. In this case, these are flash floods. So for different return periods, so 10, 50, 100 years. And on the bottom, we have our elements at risk. So buildings, for example, with the estimated costs. We overlay the information and we analyze for each element at risk what's the intensity of the hazard, and we correlate that with the vulnerability to get the expected losses, which we multiply by the costs. And so if we do that for all the buildings, we would represent for the whole area every scenario as a probability versus losses. And if we also include uncertainty, we could take any of the data sets and say, okay, this is the average and this is the standard deviation, or this is the variation of the data. We generate basically risk curves, envelopes that would say have a minimum and a maximum value. So for these risk assessments, we need basically these inputs: hazard maps, element at risk data, vulnerability curves, and we want to represent the risk as on an administrative unit map. We do not want to calculate risk for every individual building, as there is too much uncertainty in relation to the data. So we want to aggregate the results per administrative unit, as also the decision is taken per administrative unit. So these hazard maps, if we look at multi-hazards, they might look like this. This is an example from one of our test areas where we have debris flows, flash floods, landslides, and tsunami hazard, and each one for different return periods. And so you see 20, 50, and 100 years, but also the intensity could be different, so impact pressure or water depth or spatial probability in the case of landslides. So we use then two-step approach. We do first a loss analysis for all individual scenarios. So we combine, say for the flooding or the debris flow, so the landslides, we do a loss assessment for each of the return periods. And also we could do that based on land parcels or based on buildings. And then we estimate, say, the losses for each of those units. And we finally aggregate that information per administrative unit. This is used in the second phase when we go for the risk analysis. We have the whole database of losses calculated, and then we can either say we do a single hazard risk analysis or multi-hazard risk analysis, where we look at the combined effect of the different hazards in terms of the total risk. So the results could look like this. For example, on the left side, we see monetary risk. On the right side, we see population risk. And we see also the risk for the different types of hazards within the area. So you could also prioritize, like I say, we need to focus more on this particular type of hazard and on another type. We, after we do this risk analysis, we have to evaluate the risk. So this is the second component in which values and judgments are important. So it's not just the pure quantification, but it's an evaluation if a risk is too high or not. This requires standards, so risk acceptability criteria. And as I mentioned earlier, these risk acceptability criteria would be different for different countries. And many countries also did not establish these risk acceptability criteria, also because of the implications that would have if a government would establish it, and many areas would fall in the unacceptable risk, then actually the government is liable to change that, which would be, say, overly complex. When we are going further in the risk management approach, we, after the risk evaluation, and if we consider risk to be too high in particular areas, we formulate particular risk reduction strategies, risk reduction measures. And as risk is a function of hazard, vulnerability, and exposed elements at risk, and also of the coping capacity of the communities, for example, in early warning or education, we can adjust any of those to change also the risk. So we can reduce the risk by reducing the hazard, reducing vulnerability, or reducing the number of exposed elements at risk, for example, by relocation. This requires that you would evaluate what are the possible options for risk reduction at every individual location. So risk reduction strategies could be avoidance. You modify the hazard. You mitigate or reduce. You modify the susceptibility of the hazard damage, for example, by improving the vulnerability of the objects. Transfer, we use insurance or other financial means, or retention, so we accept and budget for that. So this would require a kind of circular approach where you would decide to, based on the stakeholders' requirements, to analyze the risk as it is now, based on elements at risk and hazard modeling, and then decide to formulate risk reduction alternatives. These risk reduction alternatives might affect elements at risk, and they might affect the hazards. So you need to reanalyze both of these before you could reanalyze your risk. So you would analyze the risk before you implement it, and what would be the risk if we would implement it. Then based on that, we can compare alternatives, and we can say, okay, what would be the cost-benefit ratio between these different alternatives, which one would be preferential, and what would be the other characteristics that would make that you decide upon that. And so this is a circular approach, which would actually also be needed if a major event would happen. That would also change our hazards and our elements at risk. And it would also be happening if we would look at future scenarios. So if we would say, what would be the effect of climate change or certain scenarios of population change, and how would the risk change over a number of years? And in order to take decisions on which risk reduction measures are now most appropriate, you would have to run your risk analysis for different possible future scenarios. And so in the case of these risk reduction alternatives, you could think of, for example, here an example where to protect a particular area, we could go for engineering solutions, building hard engineering structures, or actually go for ecological engineering solutions. Or we could go for a complete different approach like relocation. Each of these three would change the hazard and would change the elements at risk, and therefore also the risk. So here, the graph below shows, okay, this would be the risk before constructing anything, and A1, A2, A3 are the three alternatives, with the risk after implementation and the risk reduction. So based purely on the risk reduction, you could make a particular selection in the decision process. It would be even better actually to do a cost-benefit assessment, so where you calculate the benefit of reducing the risk versus the costs of implementing the measure itself. Now that would be require also that you put everything in monetary values and that you could both quantify the risk reduction as well as the investment and maintenance costs over a larger period of time. So that could result in an example like here, where you have different cost-benefit indicators, and you would see that the engineering solution, for example, is the best above the eco-DRR solution. Nevertheless, these are just based on costs and benefits, and there are many other factors that would also play a role in deciding that. So we need the stakeholder involvement and multi-criteria evaluation. Now, finally, we could also look at how risk changes in future scenarios. Here, some examples are given of land use change and climate change scenarios that would be, you could calculate in several years from now. So, for example, what would be a situation in 2030 or 2040? In terms of land cover maps, we could simulate that. We can do a land cover model and saying if we have no risk reduction, this would be the development. And if we would have the different alternatives, these would be the developments over time. And then calculate, say, in the long run, under which scenarios, which of the risk reduction measures would function the best. So which of the risk reduction measures is the best change proof. And so this would allow you to take really decisions that also incorporate possible changes. In order to do that, you need a lot of calculations, and it would be helpful to have tools to do that. You can actually do this with a conventional GIS. We developed it using an open source GIS, but we also developed a spatial decision support system. It's called risk changes, where all these different components of evaluating risk reduction alternatives and also evaluating future changes in risk can be analyzed. Now, these risk analysis are data demanding, so you cannot just simply run it directly there. You have to have the hazard models and so on also prepared, but this could also be done by others which uploaded it in the same spatial decision support system. So through this, I have given a rather brief overview and a rapid overview of say how you can do a risk assessment for decision making. That it's a very important tool to evaluate what would be the best risk reduction alternative, but also how risk would change in the future due to possible changes. Well, I hope this was an instructive lecture, and I'd be happy to answer any questions on your side. Finally, I'd like to thank a number of my MSc and PhD students that helped that were collaborating with me in several of the projects that I showed you. So thank you very much.
Thank you, Professor. Thank you, Professor Van Westen, for these very interesting lectures, and that give us a very nice idea and a lot of examples on the project that you have conducting. And I realize that it's the kind of research that have huge impact on our society, that protect people, right? And I just wonder if some of our students might have any questions.
Yes.
And I believe that Professor Van Westen will be glad to answer.
Sure.
Okay, let me start with my question first. You have said that there is multiple countries that that do not establish their acceptability criteria.
Yes.
And I guess that in this country might be exposed to the effect of global changes. and they are maybe the most vulnerable country for that. So that there's anything that we could do for establishing the risk for this country?
Well, it's a difference between establishing the risk or having a unified method to determine whether that risk is acceptable or not. If you would imagine that, well, a vulnerable country, which is maybe also a poor country, say an individual living in such a country could be living under problematic situations, like, for example, in a squatter area, or exposed to health effects of industry or diseases, which would make that they would have a much higher risk of being killed by disease or by an accident or something than somebody in a developed country. And so if you would then establish a risk for natural hazards and would apply the same standards as would be in developing countries, these trains to put a much higher boundary for natural hazards than you would do for other causes of death within the country. And so it must be focused on the specific situation within the country. You can, of course, always assess the risk and then say which people are running the highest risk, so where do we prioritize? Yes. Risk acceptability would say, okay, every time when there is somebody living, say, a community above the threshold of acceptability, the government is responsible to reduce risk. And that would imply so many financial implications that the government would be very reluctant to establish that.
Yeah, of course, yeah. Thank you very much.
Yep.
So we got another question from Professor Evans. He thank you very much for the excellent lectures. And the question is, can the model handles a risk such as climate change, where the risk might increase and decrease in a random way over time?
Yeah, I think there should be always a link between climate change and a hazard model. And so the decision support system that I'm showing is actually taking results from hazard models as input. It does not model how the change happens. And so that is a very important consideration. So your climate change has different effects in different areas, and that requires that people focusing on hazard models would work very closely with climate change experts to see how we can translate the effects of climate change into changes in their hazard models. To take an example, we worked in the Caribbean. The time between major events like hurricanes, tropical storms, might reduce. And so what we would need to know from climate change experts is how the probability of occurrence between two successive events would change, and that we would include in our hazard model. And so that you would have a situation there where the recovery from the previous event is still not complete before a next event would happen. And so those kind of inputs are required, say, by combined work between climate experts, hazard models, and modelers and risk modelers.
Awesome. Thank you very much. And then I have another question on a practical aspect. That a risk assessment time to time is very related to political decisions as well, and it's changing every 5 to 10 years depending on the mandate, right? And it's like global change. You can't predict that too much. Suddenly President Trump, for example, who is claiming on his tremendous victory when he's losing the House of Representatives, but when he suddenly decides to withdraw from the Paris conference, that would change totally the output of the models, right? So how we should, the models should be handled with this kind of thing that change that you cannot predict it.
Well, I think the political aspect is very much involved also in terms of the willingness to anticipate the effects of say of the changes that you foresee. On the other way, whether or not politically people are accepting climate change, this is an important issue in terms of, say, the policies that are being implemented in disaster risk reduction. On the other hand, I would say that, say, reality is actually showing also in areas of where they have reluctance in accepting that there is definitely a change required. And the impact of say hydrometeorological hazards, in particular tropical storms and hurricanes, also in US, is increasing, and you even see with the reluctance, like with Donald Trump, he's actually going back on his tracks. Let's hope that really results in a real change, and also coming back to agreement that they subscribe to Paris agreements again, create the policy of climate change adaptation.
Yeah,
definitely, it has a lot of impact on the policies to reduce the risk.
Awesome. Yeah, thank you very much. I just wonder if there is any questions from the audience. Okay, so if you have any questions, I believe that you can send an email to Professor Van Westen, or you can send to me, and then I will transfer to Professor Van Westen if it is needed to. So again, thank you very much, Professor Van Westen, for giving to us these very interesting lectures, and that give us an idea about the research that you are doing and the program that is offered from your institutions. Thank you, many thanks again, and then I'd like to thank the audience for participating, and then I'd look forward to see you guys next week. It's going to be a conference given by Professor Jan Oliver from the Kew University from the UK, and he's going to talk to us about environmental risk assessment. So many thanks, and then hope to see you next week.
Okay.
Bye.
Goodbye. Bye-bye.
Bye-bye.